Hey there, it's Shannon Matchick-Myers, and today we'll be covering section 15.7, the Divergence Theorem, from the Larson and Edwards calculus text. So let's go ahead and warm it on up. We did this a day or two ago. Find the flux of the vector field F through the surface S, where you can do that by finding the double integral over the surface of the dot product of the vector field and n, where n is the upward unit normal vector to S. All right, so on your mark, get set, go. Pause the movie. I know you can do it. Okay, let's see how you did. Well, we got a few things we need to find, right? First off, why don't we start by rewriting this surface as some g at x, y, and z is equal to, so remember, if I had subtracted that square root from both sides, I'd have something equal to 0. So I'm just going, and remember g at x, y, and z is equal to 0 for purposes of finding our gradient. So let's go ahead and rewrite this as z minus the square root of a squared minus x squared minus y squared. And then the gradient of g, del g, will be equal to, well, we've got to find our first partial with respect to x times I, minus the first partial with respect to y times j, and then it's just going to be plus 1 times k because the coefficient to z is 1. All right, so here we go. We will have negative, and then we're going to end up with a negative 2x when we're using the chain rule over the square root of a squared minus x squared minus y squared. And then we're also going to have a 2 here. A 2 from using that power rule. And this is all times I. And then minus, we will have it'll be very similar, negative 2y over the square root of a squared minus x squared minus y squared. And again, need to put in my 2 from the 1/2 using the power rule. That's times j. And then plus 1 times k. And so we can simplify this a bit. The 2's will divide out and the negatives will revert to positives. Ooh. So, making it pretty, we'll have del g is equal to x over the square root of a squared minus x squared minus y squared times I plus y over the square root of a squared minus x squared minus y squared times j plus k. Groovy? Okay, so now what do we need to do? We need to find that dot product between f, that vector field f, and the gradient of g. Cool, cool? So we will have, remember the dot product, so we're going to be doing x times x over root a squared minus y squared because we're using the coefficients here, right, for our vector field. So we'll just have x squared over the square root of a squared minus x squared minus y squared plus y squared over the square root of a squared minus x squared minus y squared times, oops, not times j, and then minus 2 times z. Good so far? Awesome. All right, so now let's see what we get. So here, simplifying, notice that we have the same, I'm thinking polars might be better for this. And so notice that we're going to have x squared plus y squared over the square root of a squared minus quantity x squared plus y squared, all under the radical. And then we still have minus 2 times z, but what was z? Z was equal to the square root of a squared minus quantity x squared plus y squared. Good so far? Awesome. So now, if I get a common denominator here, right, aren't I just going to be multiplying by a squared minus quantity x squared plus y squared over, and that's a radical, a squared minus quantity x squared plus y squared? Cool so far? So that's going to give me x squared plus y squared, remember, is r squared, and then over the square root of a squared minus r squared. And then the radical will go away, and so here, continuing, we'll have minus 2 times a squared minus r squared. So this is the common denominator for the whole deal there. Okay, so then that will give us r squared plus 2r squared will give us 3r squared, and then minus 2a squared, good, over the square root of a squared minus r squared. So I'm going to go ahead and add another page in. Sorry about that. I didn't leave enough room. So now we figured out the dot product, and we are going to need to do some other stuff. So here we ended up with, just to remind you, f dot del g was equal to 3r squared minus 2a squared over the square root of a squared minus r squared. So now what we need to do to find the flux, right, we need to figure out our region. And so do you see that we basically have in that radical, we've got a squared minus r squared, or if you want to think about r squared as x squared plus y squared. And so that's got to be less than or equal to a squared in order for us to get something real when evaluating that square root. So if you just took a look at this as a, and then you made that circle. That didn't work out well. Okay, let's see. Well, I didn't make my scale very well. I'll just make some big ordered pairs, all right? So those are where we'll meet. So basically this region R inside here, this is what we'll be using for our bounds when we turn this into polar coordinates. Alrighty, so here we go. Theta is going to be going from 0 to 2 pi, and then we're going to have R going from 0 to A. And so we're going to end up having R from the formula converting to polar, and then times 3r squared minus 2a squared over the square root of a squared minus r squared dr d theta. Let's go ahead and pull apart this integral. Let's just consider the integral from 0 to a of, I'm going to make this two integrals. We're going to have 3 on the outside, r cubed times a squared minus r squared to the negative 1/2 dr minus 2a squared times the integral from 0 to a of r times a squared minus r squared to the negative 1/2. So this is with respect to r. So both of these are improper because we're going from 0 to a, and notice that you would get a on that upper limit, you get a vertical asymptote. So this is what we're going to do. We are first going to consider, the first one we'll have to do an integration by parts, but we're going to consider first the improper integral from 0 to a of r times a squared minus r squared to the negative 1/2 dr. Cool so far? So this is going to be an improper integral. We're going to need to evaluate the limit as if we're going from 0 to a, if we call it going from 0 to t, t's got to approach a from that left side, okay? And then we're still integrating r times a squared minus r squared to the negative 1/2 dr. So that will equal to negative 1/2 times the limit as t approaches a from that left side of the quantity a squared minus r squared to the positive 1/2 divided by positive 1/2. And we're going to have r going from 0 to r going to t. So the 1/2s will divide out. We'll just have this negative on the outside of the limit. And then we will have a squared minus t squared to the 1/2 is our upper limit, minus a squared minus 0 squared to the 1/2. So that will end up being, the limit will not affect the second one, and we can just go ahead and plug a into the first one now. So because there's no denominator we have to worry about. So this will be negative a squared minus a squared to the 1/2 minus a, which will be positive a. Now that we've gotten that taken care of, let's go ahead and take a look at, so that we're going to utilize this soon. So now that we have that kind of basic integral down, let's now take a look at this one here that we're going to have to use integration by parts on. So on, I don't know, I'll use this color, I guess. So on this one, we got to use integration by parts. So what'll happen is on our integration by parts, we're just going to consider the indefinite integral right now. And so that will end up being, we have r cubed, the integral of r cubed times a squared minus r squared to the negative 1/2 dr, right? Got to add another page. And then we will have, if we have our, we're going to have our u equal just to r squared because we need an r to integrate the second part. So u is equal to r squared. Du will be 2r dr. dv is going to equal to r times a squared minus r squared dr. And so v will just be, we've done a similar one up there, is just going to be what? Good. We'll have negative 1/2 because we got to balance it when we integrate, right? We have to have a negative 2 to integrate. And then we're going to have a squared minus r squared. I'm sorry, that was to the negative 1/2 to the positive 1/2, and that's divided by 1/2. And so v is going to be negative a squared minus r squared to the 1/2. Good so far? Okay, so plugging that in, we will have the integral of, or no, sorry, u times v. So that would give us negative r squared times a squared minus r squared to the positive 1/2. And then we're going to have minus the integral of negative a squared minus r squared to the 1/2 times 2r dr. It's just integration by parts. So now, do you see that second integral is all set up to integrate because we have our negative 2r. So that's going to be negative r squared, and then we'll have a squared minus r squared to the positive 1/2 minus a squared minus r squared to the 3/2 divided by 3/2. I'm not going to put the plus c because we're going to be evaluating it. And so we will have negative r squared times a squared minus r squared to the 1/2 minus 2/3 times a squared minus r squared to the 3/2. Groovy? So now, here we go. Notice that if we had substituted the, anything in, there's no limitations on approaching some number approaching a from the left side. So we're all good to go in evaluating this. So now let's take a look. The integral from 0 to a of r cubed times a squared minus r squared to the negative 1/2 dr, I'm just cleaning it up, is going to equal to what we found here, negative r squared times a squared minus r squared to the 1/2 minus 2/3 times a squared minus r squared to the 3/2, and that's all going from r equals 0 to r equals a. So that will give us, when r so that will just, I'll just put it in. So we'd have upper limit of integration would be negative a squared times 0, right? To the 1/2 if you want to, because a squared minus a squared is 0, minus 2/3 times 0 to the 3/2, minus, if r is 0, we'd have negative 0 squared times a, because if r was 0, you just have the square root of a squared, which is a, but it all zeroes out anyway. And then minus 2/3 times a cubed, because that will have a squared to the 3/2, which will be a cubed. Groovy? All right, cleaning that up, the whole first part zeroes out, and we end up with a positive 2/3 a cubed for that part. Groovy? So now let's put this all together. This is going to end up being, the first integral needs to be tripled. The second integral needs to be multiplied by negative 2a squared. So from our first result, so this will end up equaling to 3 times what we got in the blue, and we got in the blue down here 2/3 a cubed, and then minus 2a, oh, that was supposed to be a cube, right? Yep, sorry. That was, where was it? I can't find it. Here we go. Cubed. There we go. And then minus, we had pulled out a 2a squared, and then when we had done that very first improper integral, we had gotten positive a. So we will have, this will end up equaling to 2a cubed minus 2a cubed, which is 0. Well, that was a lot of work for nothing, huh? So so the second integral will zero out anyway. So so basically, remember where all this came from. We had done, I did the colors matching those integrals, but after all this work, we get a 0 for that one. So if you take a look at this integral, right? So all this right here, think of it as a scratch. What's going to happen is we're going to get equals the integral from 0 to 2 pi of 0 d theta, which is just 0. That's our answer. That was mean. Bad teacher. All right. Well, cool. Well, we got that done. That was a good review of improper integrals and integration by parts, right? So let's take a look at Gauss's theorem, which is the divergence theorem. So Let Q be a solid region bounded by a closed surface S oriented by a unit normal vector directed outward from Q. If F is a vector field whose component functions have continuous partial derivatives in Q, then it turns out integral over the surface of F dot n ds is equal to the solid region, the integral over the solid region Q of the divergence of F dV. So this is kind of cool. It's very reminiscent to, what was it, Green's theorem, where if you knew, a certain area formula, you could make this way easier, right? So let's take a look at some problems. Hopefully the warm-up was the worst one. So let's do it. Our first task is to verify the divergence theorem by evaluating the integral over the surface of the dot product of the vector field F times the unit normal vector that's directed upward, ds as a surface integral and as a triple integral. All right, so we're going to do it the easy way and the hard way. So we're going to need a couple things for here. Where is it here? Sorry. Recall that the divergence of F is equal F that at x, y, and z is equal to the first partial of m with respect to x plus the first partial of n with respect to y plus the first partial of p with respect to z. So we'll be utilizing that in the second part. So it's kind of like one of those things. We'll probably have an easy way and a hard way to do this. So we've got the vector field is xy times I plus z times j plus quantity x plus y times k. And the surface is bounded by the planes y is 4, z is 4 minus x, and the coordinate planes. So let's just kind of think about what does that look like. So if you have, this situation here. It's nice to have a picture of what's going on, right? So we'll be having, let's see. So y equal to 4, z is 4 minus I. So lots of 4s here, right? So we need 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, and 4. So the line y equals 4, right, would just be this line here. Shift it over. Cool so far. So that's the line y equals 4. And then, we've also got the axes, right, are included. So the line y is 0 will be included. These are supposed to be parallel. Hopefully they look relatively parallel. And then, and so for our other one here, so that one we were working with y is 4. So if z is 4 minus x, right, what's going to happen is, sorry about the dogs, what's going to happen is y can vary, right? since it's not pictured there. So we'll bound that at y is 4. And so if we do this line here, if x is 0, z is 4. If z is 0, x is 4. So we're going to end up with this. And then we'll also, have point somewhere about here. Oh, sorry. Something like this. Groovy so far? And then finishing off the picture, we would have, let me just finish it off. We'd have this and this. Whoops, sorry. And then down to here. Groovy? So that's what that's what it's gonna look like. So basically we're gonna be just utilizing, we don't have to worry about the stuff that goes behind because it's been bound by the axes. Groovy? So our shape is very beautiful. And not the best shader person. It might be a little shady, but shading isn't always my thing. But this would be our solid here, something like this. Okay, so anyway, that's what we're working with. So let's check it out. So what's going to happen here for we'll have different surfaces. So if we look at surface 1, right? Surface 1, we would have z is 0, n, okay, because the one pointing up, the normal vector pointing upward is going to be negative k. So f dot n is going to be negative quantity x plus y. Okay, so that's surface 1. So what we'll have is we'll have negative the integral 0 to 4 of x plus y dx dy. X, varies from 0 to 4, and then y varies from 0 to 4. So that's going to be negative integral 0 to 4. We'll have x squared over 2 plus xy. That's x going from 0 to 4. We still have our dy hanging out. So that will be negative integral 0 to 4. We'd end up with what? 8 plus 4y. Or sorry. Yeah, 8 plus 4y. dy. And then that would end up being negative 8y plus y squared, going from y is 0 to y is 4, which is going to give us, oh, sorry, that would be 2y squared. Not all of that 4 was divided out. So 2y squared. So then when y is 4, we would get, let's see, negative 64. The lower limit will zero out. Cool so far? Surface 2 is going to be, so now what are we going to do? We're going to have y equal to 0. And so n is going to be negative j. Okay, to stick it outward. So then what will happen is our dot product of f dot n will end up being, so f, remember, everything, let's see, it would be negative z, because that j is the only one that would stay. Others are 0. So that would be negative z. So this one will be the integral from, again, we'll have a negative from that negative j, or from the negative dot product. So we'll have, we're going from 0 to 4, and we're going for z, or for x, okay? And then for z is going to go from 0 to 4 minus x. And again, we'll have our z here, and we'll be going dz dx. Cool, cool? So that'll be negative integral 0 to 4. We'll have z squared over 2. And that's going from z is 0 to z is 4 minus x. So that's going to be, can bring out a 1/2 here, integral 0 to 4 of quantity 4 minus x squared, and there was a dx here, sorry, dx. Cool, cool? Integrating that, I just need to adapt by a negative, and we're going to end up with 1/2 times 1/3 times 4 minus x cubed, where x is going from 0 to 4. So that's going to be 1/6 times 0 cubed minus 4 cubed. And that was 1/6. And so that would be negative 64 over 6, which will be negative 32/3. Good so far? All right, and so we have many more surfaces to go because we've got to get those normal vectors sticking out. So here, as we continue, we'll do a different color. So for surface 3, so what have we done so far? We've let z equal to 0. And so we've got a unit normal vector pointing out from the bottom of our shape here. We've let y equal to 0. So we had a unit vector pointing out from that triangle that's kind of this one here, that triangle. And so now what do we need to do? We need to let y equal to 4, right? So now we'll have a unit vector pointing out from this triangle. Cool with that? Okay, so it'll be similar. So actually we can do surface 3. Y equals 4. So that means that n is going to be j, and f dot n will be equal to positive z. So let's do it. We'll have the integral again from 0 to 4, 0 to 4 minus x. We're going to do dz dx again. So this will be z dz dx. We just did this one. It's going to end up being the opposite of what we just got, right? So it'll be the opposite of negative 32/3. which is positive 32/3. That was easy. All right, our next surface will be when x is 0. So it'll be pointing out from the bottom of the, it'll be pointing out from the back, actually, of the shape here. All right? So, continuing, we will have surface 4 will be when x is equal to 0. So that means n is going to equal to negative I. And so the dot product will equal to negative x times y. So, because remember, in our that was the coefficient to the I term in our vector field. So we will have the integral over our region of negative x times y dA, but x is equal to 0, isn't it? So wouldn't that just be 0? So that was easy. So now surface 5 will have, what color shall we use this time? So surface 5, we're going to take care of the xz. So we have z is 4 minus x, which means x plus z is 4. So now the region we're going to be working is going to be like this one right here, that xz. Groovy? All right, so now we will have a little more work. So if we let g of x, y, and z equal to z plus x minus 4, because remember z was equal to 4 minus x, and so I'm basically saying z minus 4 plus x is 0. And then I'm setting that g, x, y, and z equal to 0. So del g is going to be equal to what? I plus k. Good. And the magnitude of del g is equal to 1 over root 2. Right? So n will be equal to 1 over root 2 times I plus k. Cool so far? So the dot product of the vector field with the unit normal vector is going to be 1 over root 2 times xy plus x plus y. And so our integral, therefore, will be equal to this integral over s. It's a little more complicated, of 1 over root 2 times xy plus x plus y. And remember, you got to multiply it by the magnitude. Now this comes from the fact that, okay, so now that in turn will be equivalent to, the root 2's will divide out to be 1. And so this will be the integral from 0 to 4 and 0 to 4 of xy plus x plus y, and that's going to be dy dx. Okay? So we will have the integral from 0 to 4 of xy squared over 2 plus xy plus y squared over 2. From y is 0 to y is 4. And then that will be the integral from 0 to 4 of, let's see, when y is 4, we would get 8x plus 4x plus 8 dx. Sorry, there's a dx here. That will end up being equal to the integral from 0 to 4 of 12x plus 8 dx, which will be 6x squared plus 8x, going from x is 0 to x is 4, which will give us 96 plus 32, which is 128. So now, to find the divergence, what we have to do is sum up the result of the integrals of all those surfaces. Okay, so we'll end up with, at the end of the day, so therefore, the integral over the surface of f dot n ds is going to equal to, so remember we had all these different ones, so our S1 was negative 64. So negative 64, and our next one we had, the purple one was negative 32 thirds. So minus 32 thirds. And then the third one was plus 32 thirds. That fourth one was 0, so plus 0. And our fifth one was 128. And so at the end of the day, what do we get? We'll end up getting 64. Cool, cool? Okay, so now let's go ahead and use the divergence theorem. Okay, so for the divergence theorem, remember what we're doing. Let's go look at it again because it's been so long. Oops. Yeah, it's up here. So for our divergence theorem, what we're going to be doing is this. We just need to find that dm dx plus dn dy plus dp dz. That's for the that's what we'll put in the integral, and then we just need to make an iterated integral for the volume, okay, or the solid rather. So let's do it using the so this is that first one was the hard way, right? So this was the old way. And the new way would be, all right, new way, using the divergence theorem, is our integral over S of f dot n ds is going to equal to, it'll be a triple integral. We need to find some more stuff, right? So it would be of dm, first partial of m with respect to x, plus the first partial of n with respect to y, plus the first partial of p with respect to z. And then that would be dv. So this is our region Q. Okay, so let's see. Actually, let's switch this a little bit so we have more room. So this would go up to here. All right. So, well, what do we have for our stuff here using our divergence theorem? Let's take a look at, so M, I'm looking at the vector field, is equal to xy, n is equal to z, and p is equal to x plus y. So here, do you see that all we're going to be left with is dm, the first partial of m with respect to x, because there's no y's in n and there's no z's in p. So, I mean, if you need to, you can. We can say the first partial of m with respect to x is equal to y, right? The first partial of n with respect to y is 0 because there's no y's in there. And the first partial of p with respect to z is also 0. So we will have this will equal to the integral from 0 to 4, 0 to 4, and 0 to 4 minus x of y, that's the divergence of f, dz, dy, dx. And I'm not going to go through and work that triple integral. I have absolute faith that you can do it. I promise it turns out to be equal to 128, and it's much easier to do. Cool, cool? All right, so now let's go ahead. Use the divergence theorem to evaluate the surface integral of f dot n ds and find the outward flux of f through the surface of the solid bounded by the graphs of the equations. So here we go. Our vector field is xyz times j, right? And so if we take a look at this, m is 0 because there's no I, n is x times y times z, and p is 0 because there's no k. So the first partial of n with respect to y is x times z. So now we need to figure out our bounds. So the divergence, this tells us that the divergence of f is equal to xc. And we have this other information here, right? So if you look at x squared plus y squared is equal to 9, right? Let's think about how we want to do this one. If we want to do, I don't know, it doesn't really matter if you start with dx or dy, but it's going to be best to start with one of them. So why don't we just do dx, dy, dz? So if you isolate x, do you see you'll get plus or minus the square root of 9 minus y squared. Cool so far? So y, therefore, is going to be bound between -3 and 3 because the radius of that circle is 3. And z is going to be bound between 0 and 4. So we would just go and say that the integral over the surface of f dot n ds will be equal to the triple integral over the solid Q of xz dv. Well, that's going to be the integral from 0 to 4, negative 3 to 3, and then this one will be negative root 9 minus y squared to positive root 9 minus y squared. And then we have xz, and the way I set it up, it's dx, dy, dz. Groovy? Okay, so we will get, this will equal to the integral from 0 to 4, the integral from negative 3 to 3, and then we'll have what? X squared z over 2 when we do the integration. So we'll say this, z over 2 times x squared, where x is going from negative root 9 minus y squared to positive root 9 minus y squared. And so we'll integrate 0 to 4, negative 3 to 3, and then we will have, when I square x, I'll end up having z over 2, and we'll end up having, let's see, 9 minus y squared is our top limit of integration. Let's square away that radical. And then minus, it'll square away the negative, so again I'll have 9 minus y squared, which is 0, right? So that means the whole thing has to be 0. And so the outward flux of F through the surface of the solid bounded by the graphs of these equations is 0. Groovy? All right, so now we want to, same instructions, all right? So let's take a look at what we got going on. So now, this one will be a little more involved. We have, an M, an N, and a P. So let's start with that. M is equal to, I'll just have the 2 with each of them. And so dm dx is 2. N is equal to 2y. So dn dy is 2. And p is equal to 2z. So dp dz is 2. So when I square each of these and add, or no, I don't need to square them. So when I add these together, do you see that I will have 6? Okay, so that makes the divergence of F equal to 2 plus 2 plus 2, which is 6. So that's pretty cool. I mean, what is this surface anyway? You've got z is 0, right? And so here I'm thinking that looking at all of this here, z squared would be 4 minus x squared minus y squared, which would be equivalent to x squared plus y squared plus z squared is 4. But since z, we're also bound by z is 0, right? This would be the upper half of this sphere, right? Well, what is the volume of a sphere? The volume of a sphere is 4/3 pi r cubed, and that for us, r would be, that means r is 2, right? So r is 2, so that would give us 32 pi over 3. Good so far? And so we need to cut that in half, right? So the volume of the hemisphere would be equal to half of that. Which would be 16 pi over 3 for us. So that means we would get what? So that means our integral over our surface of f dot n ds would be equal to 6 times the volume, which is equal to 6 times 16 pi over 3, which is going to be 32 pi. Cool, cool? All right, so I believe that wraps it up. Yeah, this is just a graph I mistakenly put at the end, but it's pretty groovy, right? Yeah, so anyway, we're all done with the guided notebook. And I hope you have a wonderful morning, afternoon, or evening whenever you're watching the show. And if you like what I'm doing, hey, please subscribe and tell all your friends. All right, take care. Bye.